Hello everyone. So today's topic will be on the Euler's identity, and it is considered as one of the uh, most beautiful identity in mathematics, and it leads to an equation that is called the most beautiful equation in mathematics. So we are going to discuss about some properties and obviously the proof of Euler's equation, that is what does that mean actually. So at first, the Euler's identity consists of some e to the power I theta. Before writing about the identities, we are just considering it as x plus I y. So we are going to find the values of x as well. We are going to find the values of y. That is what are those x and y that will consist in the Euler's identity. So before moving to the e to the power I theta part, we will just consider the e to the power x function. That is a real valued function, e to the power x. So what the unique property it has? So it has a unique property that d dx of e to the power x is basically e to the power x. That means if we just differentiate the function e to the power x, we will get the same function here. And what are the other properties? Let's say e to the power kx. Here k is any constant. It can be a positive constant, it can be a negative constant, anything. So e to the power kx, then if we just differentiate the function e to the power kx, we'll get k e to the power x. So this is an important function, and its derivative is also important, because for the time being we are considering e to the power I as e to the power ix as a function, where we are considering I as a constant. Yes, obviously I is basically root over -1, so it's a constant. So this obviously holds the same property, that is d dx of e to the power ix will leads us to I times e to the power ix. So how we can derive the Euler identity using these three ideas? Let's consider a moving argument, moving particle argument. Let's a particle is moving and is position vector, or the position at any point t is represented by zt. So zt is going to be the position of a particle at time t. So z is going to be the position of a particle, and obviously vt, that is the velocity of that particle. So it is representing the velocity. Sorry, this is not the position. It will be the velocity of that particle at time t. So we just considering two properties here. The first one is zt, that is representing the position of a particle, and vt, that is representing the velocity of a particle. So we are considering velocity, so it obviously have some direction here, because speed has no direction, but velocity has obviously a direction. So now using this identity, we will just going to prove what does that mean. Let's say the particle's motion is something like this. Let's say the particle is moving along this path. So from this point to that point. Let's say at time t, the particle is at this point. So this vector is going to be z of t. Let's say this is our initial point, or the position of a particle at time t. Then this is zt, and at time t plus del t, let's say some delta time later, the particle movement will be in this point. So this vector is going to be t plus del. So the initial position vector was zt, the final position vector was zt plus del. So we'll also get a position here, and this position will be, let's say, m. So from vector addition, we can say that zt plus m is going to be zt plus delta. So from here we can say that m is equal to zt plus delta minus z of t. So what do we have the idea of instantaneous velocity? Instantaneous velocity is basically that type of velocity, that means limit delta tends to 0, that is if this value is getting closer to 0, that means if we are considering two positions pretty close to one another, then what will happen? If we are considering this is one position, this is the initial position and this is the final position, and if we consider these two positions pretty close to one another, then we will get the instantaneous velocity. That means z t plus del minus z t divided by del, as delta tends to infinity. Then we get limit delta tends to 0, and this is exactly m divided by delta. So we can call it as velocity at time t. So this is the velocity at time t. That means as we are considering delta tends to 0, so this will be represented by the velocity of that particle at time t. But look at this equation or this property. Can't we say that this is the basic definition of a derivative of a real valued function? Or for the time being, we are considering this z of t as a real valued function. So here, this is the basic property or the basic definition of a derivative of function z with respect to t. So we can say that d dt zt is going to be this. So what do we get? Finally, we get v of t, that is velocity of a particle, is basically differentiation of the position vector. Now, our main goal is to derive the Euler identity, which involves some properties like e to the power I theta or some function like e to the power I theta. So eventually here we will try to impose, or we will try to consider something similar to e to the power I theta. So let's say z of t is equal to e to the power I t. So we are considering the position vector of a particle is moving as e to the power I t. We don't know how e to the power I t moves, but yeah, we are considering the particle's position vector will be same as e to the power I t. Then from here, v of t will be d dt of zt. So from this property, from this one, we can say that this is basically I e to the power I t. That means I times, sorry, not v of t, z of t. So as the initial position vector is at t is equal to 0, z of 0 is basically 0, sorry, 1, z of 0 is basically 1, and from here v of 0 will be I. So from our previous video, we can say that if we just multiply any number by any complex number, then that number's angle will be rotated by the angle multiplied by a complex number. So what does that mean? Let's say e to the power, we are considering two functions, that means two complex number a, b. So it's new modulus. So modulus of a, b will be modulus of a times modulus of b, as well argument of a, b will be argument of A plus argument of B. So using this property, we can say that these two are basically at the right angle. How? Because one is our initial position vector. If we are considering this as, so one is a real number, so obviously positive real number, so that is going to be in the positive real axis. So this is our one vector, and the velocity is I. That means it is basically pointed just upward. Okay, so from here we can say that from initially the particle is moving upward. So at t is equal to 0, our position vector is on the real axis and our velocity vector is moving directly upward, that is 90 degree to the position vector. So from the initial phase, we can say that the velocity is directly pointing upward. So we'll now prove something later. Let's say our position vector, any position vector, let's say we're considering this one, that is a position vector is, okay, let's say r is representing a position of a particle at time t, and its modulus is always a constant. So it's basically representing a circle. And now from here we can say that r dot r is equal to k, and then after differentiate k square, sorry. So after differentiating, this will be, so all these things are vector and k is basically scalar. So r dot dr plus dr dot r, as k is a constant, so after differentiating it will be 0. So this will be 2 r dot dr is equal to 0. And from here we can say that r dot dr is equal to 0. That means position vector and its derivative, that is if we consider r as a position vector, then dr is the derivative of its position vector. Then we can say that the position vector and its derivative will always be at a right angle. From here we see that v of t is basically d dt of zt. So initially we can say already see that our zt and vt at t is equal to 0 are perpendicular. But by this property, we can say that if the velocity, if r vector and dr vector are always be at right angle, then we can say that the particle will move along the circumference of a circle of radius k. So why we are considering this property? V of t is equal to d dt of zt, and d dt of zt is basically I times zt. So if we are considering zt as a complex number, then we can say that v of t is basically I times z of t, and as we are multiplying a complex number with I, so it will rotate the position or rotate the position vector to 90 degree. So from here we can see that if zt is basically to the power it, then we can say that vt and zt is going to be perpendicular every time for all t. So from here we can say that as the position vector and its derivative are always at a right angle, so we can say that the particle is basically moving along the circumference of a circle. So obviously this z of t will also move along the circumference of the circle of radius k, but we don't know what is the value of k is. It can be less than 1, it can be greater than 1, it can be really large values and others. So we are just going to find this value, that is the k value. So what we already know? We already know that z0 is equal, z0 is equal to I times 0, that is 1, and that means as this is a constant and at z equal to t is equal to 0, the particle's position vector, the length of the particle's position vector is basically 1. So we can say that our modulus of zt is going to be 1. So what does that mean? That means that the particle will move along the circumference of the circle of radius 1. So we just identified that if z of t is going to be e to the power it, then this particle motion will be on the circumference of a circle of radius 1. But that doesn't mean our Euler's identity is already proved. We need to do a several things here. What are the things? So as we know that z of t is equal to 1, so we also know that v of t will be, the modulus of v of t will be 1, because you know v of t is basically I times z of t. This v of t is basically I times z of t, and I times z of t, that means we are considering AB, then the modulus of AB will be modulus of A and times modulus of B. So modulus of ZT is 1 and modulus of I is basically 1. So we can say that particles velocity will always be, particle speed will always be 1. As we are considering the modulus, so it is representing the speed, not the velocity, because in case of velocity, it has to be a direction. So what you know already? So we already know that arc length, as the particle motion is not on the straight line, we have to consider the arc length because the particle is moving along the circumference of a circle. So the arc length will be speed times the time t. We know that our speed is going to be 1 for that particle just because modulus of v of t is going to be 1. So that's why this is representing arc length. We can represent arc length by s, then s is equal to t. Again, there are another formula for arc length. So our arc length will be radius of a circle, radius of the circle times the angular distance. So radius of our circle is going to be 1 just because z of t is 1. So our arc length s is going to be angular distance equal to the angular distance theta. So what does that mean? We are on the verge of proving Euler's identity. So what does that mean? So let's the first one, that is, so we can say that after time t is equal to theta, after time t is equal to theta, the particle will move an angular distance. So the particle will move a distance theta around, this distance is basically the angular distance around the unit circle. So what do you get? After time t is equal to theta, that means if we are considering the circular path, that means we are considering the particle movement of the particles movement zt. So let's say this is our circular motion. That means our particle is moving around this circle. So this is our initial position. Sorry. So this is our initial position, and here we can consider it as z of 0, and our velocity vector will be something like this. So this is v of 0 is equal to I, and that is z of 0 is equal to 1. So after, let's say this is after time t. So this is our z of t is equal to e to the power I t. And obviously our velocity vector will be something like, if we are considering this as z of t, then our velocity vector will be something like this one, that is v of t is equal to I times z of t, and then after time t, it will also move an angular distance theta. So what we get from here? So the particle is at this point after time t. So let's say we are just taking a perpendicular line over here. This distance is basically 1. This is basically 1 unit distance. And then we can say that if you are just taking the vertical component and horizontal component, then we'll get this is our cos theta and this is our sine theta. So after time t is equal theta, we eventually get e to the power I theta is equal to, this is our complex plane and this is our real axis, imaginary axis, and this is our real axis. So after time t is equal theta, we get cos theta, that is the real part, plus I times sine theta. That is our beautiful Euler's identity. So this is the some analytic or some particle argument proof of this property. So from here we can say that, let's say e to the power I pi. So we are considering the values of theta as pi, then we get cos pi plus I sine pi. So the value of sine pi is 0, so eventually we get e to the power I pi is equal to -1. That means e to the power I pi plus 1 is equal to 0. So this is the most beautiful equation in mathematics. So what does that mean? That means e to the power I pi, that means we are considering a pi degree rotation. This is -1, that means what we are going to get from here, that is, if 2 is a scalar, if we are just multiplying it with -1, then we get -2. That means in the real axis, if we are considering this point as 2, then -2 is in the just opposite direction, that is in the in the negative real axis. Then we consider a 180-degree rotation. So how this rotation is happening? This rotation is happening we can just directly prove it by Euler's identity, that if we are considering e to the power I pi, we are getting -1. So if we are multiply something, multiply any complex number on the real axis, let's say z is equal to a by e to the power I pi, then we will get -a. That means it will basically rotate the points A 180 and then transform it from positive real axis to the negative real axis. So this is one of the most important equation in mathematics. We can also prove it in another way. Let's say we're just considering it a bit. Another approach. So our goal is to prove the Euler's identity. We already know that our Euler identity will be E cos theta plus I sine theta. So this is equivalent to prove that e to the power minus I theta times cos theta plus I sine theta is equal to 1. So if we can just prove this identity as equal to 1, we can also find that e to the power I theta will be equal to cos theta plus I sine theta. So let's, for the time being, say that f of theta, we don't know what is the values of this because we want to prove it, and the value of this function is going to be 1. So for the time being, we just say that f of theta is basically e to the power minus I theta times cos theta plus I sine theta. Then from here, if we just take the derivative of the function f of theta with respect to theta, then we have to use the UV integration method, and then we get e to the power I theta minus I theta actually cos theta. This will be minus sine theta plus I times sine theta. The differentiation of sine theta will be cos theta, and again this should be minus I e to the power minus I theta, and again cos theta plus I sine theta. So from here, if we are just take the e to the power I theta as common, then we get minus sine theta plus I cos theta minus I cos theta minus I square sine theta. So eventually this will cancel out, and obviously minus I square is going to be plus 1, just because I is equal to root over minus 1, I square is equal to minus 1. So minus I square is equal to plus 1. So these two will obviously cancel out. So every terms are cancelling out, so we are getting 0 from here. So we consider f of theta as a function of theta, and after taking the derivative with respect to theta, then we get a 0. That means our f of theta is a constant function. So we can say that our f of theta is a constant function. So f of theta is constant. So our first goal is achieved, because we want to prove that this function's value is equal to 1. And from here we can say that already we get some constant, but we need to fix that the value of k can only be 1. So how can we say that? So our f theta is going to be this. Then at theta is equal to 0. So if we consider at theta is equal 0, then what we got? F of 0 is equal to e to the power minus I times 0 cos 0 plus I sine 0. So this will cancel out. Eventually from here we got 1, and from here we also get 1. So our value of f of 0 is going to be 1. So in the previous statement we said that f of theta is a constant function, and this is a one variable function, and if we just graph it, it will be something like, let's say, a constant function. So something like this. So every time its value is going to be same. So now, as we find that at theta is equal to 0, the value of f of theta is 1. So we can obviously say that f of theta is equal to e to the power minus I theta times cos theta plus I sin theta is basically equal to 1. So from here we can find out the Euler's identity, that is e to the power I theta is equal to cos theta plus I sin theta. Okay. So this is another approach to prove the Euler's equation, and obviously from this Euler equation we can also find some expression for cos theta and sin theta with respect to e to the power I theta, and this expression are something like cos theta is equal to e to the power I theta plus e to the power minus I theta divided by 2, and sin theta will going to be e to the power I theta minus e to the power minus I theta divided by twice I. So we just need to consider this is e to the power I theta, and we need to consider it e to the power minus I theta will be cos theta minus I sin theta. So eventually if we just replace theta by minus theta, then by even and odd function consideration, cos is an even function, so it will be cos theta, and sin is an odd function, so it will be minus sin theta. So from here we get these two properties. Now, another thing is that initially in the first lecture we said that we can represent a complex number in the Cartesian coordinate system. So let's say this is the Cartesian coordinate system in polar as x plus iy to r theta. But from now on, we're not going to write this down at r angle theta. We will just take it as r e to the power I theta, because we know the Euler's identity. And if we are just considering this as something like this, let's say this is our point x plus iy, and this is going to be our modulus, that means r, and then this is our theta. So we can say that this is r cos theta taking the horizontal component, and this is r sin theta taking the vertical component. So from here we can say that z is basically r cos theta plus I r sin theta. So it is very easy to verify from here that we can just write down this as r times e to the power I theta. So it is more convenient to write the polar form as r e to the power I theta other than r angle theta, because it will just answer almost everything. Because let's say z1 is equal to r1 e to the power I theta 1, and z2 is equal to r2 e to the power I theta 2. We can see that if we just multiply these two numbers, then we are getting r1, r2 e to the power I theta 1 plus theta 2. So our argument that we already proved in geometrically, that if we are taking the multiplication of two complex numbers, then their modulus will be multiplication of their individual modulus, and their angle or the argument of the multiplication of z1 z2 will be argument of z1 plus argument of z2. It is making more sense here after just involving the Euler equation. So from here we can also prove the de Moivre's theorem. So from here we can also prove the de Moivre's theorem. Let's say z1, we are considering the multiplication of complex number up to zn. Then what do we get? r1 times r2 and up to rn e to the power I theta 1 plus theta 2 plus and up to theta n. So we are taking the multiplication of n complex numbers in polar form. So they are taking this form. Now, if we consider all these n complex numbers are exactly the same numbers, that means if so if z is equal to z1 is equal to z2 and equal to and up to zn, then we can say that this is basically, so z to the power n is exactly r to the power n e to the power I n theta. So from here we can say that we are just substituting the polar form of z, that is r e to the power I theta to the power n, r to the power n e to the power I n theta. So e to the power I n whole to the power theta is equal to e to the power I n theta. So after just considering the Euler's identity, we get, sorry, this should be, there is a mistake here. So this should be e to the power I theta to the power n. Now cos theta plus I sin theta n is equal to cos n theta plus I sin n theta. So the proof of de Moivre's theorem was a bit complex before the invention of the Euler's theorem, Euler's identity, but we can just use the Euler identity to find the short proof, or you may call it as a simple proof of the de Moivre's theorem. So, okay, that's it. Today's lecture is going to be up to this, and in the next lecture we are going to discuss some basic algebra on complex numbers. Till then, thank you.